Hello folks, in this video I am going to describe a characteristic equation corresponding to the notion of eigenvalue and eigenvector. So as usual I am going to start with a square n by n matrix. I am going to have an eigenvector which is described here as a column x1, x2, x sub n. And I'm going to assume that that corresponds to eigenvalue c, that is a times x is equal to c times x. So when you do this kind of thing, you are going to notice that you can actually subtract. So you can write the equation as a times x minus c times x is equal to 0. Now remember that in this case 0 is 0, 0, 0, 0, but I'm going to write simply the column, a big O to represent that 0 column. Alright, so when you get that, you can also write equivalently a times x minus, and now in order to be able to factor the matrix x, I would have to have a matrix that is an n by n matrix. So I'm going to say c times I sub n times x. Again, why do I do that? Because I want to factor x here, and I want to say, you know, this is the same as a minus c times I n times x. And in order to factor x, in order to be able to subtract here, I would have to say an n by n matrix minus an n by n matrix. If I simply left c here without this in, I would have to say a minus c, and that would not make perfect sense because I am subtracting a constant from an n by n matrix. So I would have to do that, and I'm going to say, well, this is equal to 0, so my equation, the one for the eigenvalue, really becomes this one over here. So here's what happens. This equation would have to have a non-zero solution. Remember that x is not assumed to be the zero column. If this equation has a non-zero solution, it means that this matrix over here that I'm underlying, a minus c times in, is not invertible. Because if it were invertible, I could simply say, from this equation, I could simply divide out or multiply by its inverse, right? So multiply by its inverse is what we informally say divide out by this guy. So if it were invertible, I would simply divide out and I would conclude that x has to be 0, 0, 0. That's not the case. So, so what I want here, I want a minus c times in be non-invertible. And this is invertible. And this is very important because this is a sufficient constraint to find C most of the time. So saying that a matrix is non-invertible is the same as saying that the determinant of A minus C times In is equal to 0. So this is an equation because the determinant of a matrix is a number, and I set this number equal to 0, and I solve for C. So that's going to give me an equation that I solve for C. So this equation, the equation determinant of A minus C times I sub n equal to 0 is called the characteristic equation of, attention, A, the matrix A. So that essentially will find me all the possible eigenvalues if there are any by solving this particular equation. Now this is not particularly enlightening, this abstract formulation, so what I'm going to do next, I am going to write an example over here. As usual, I am going to select and delete the stuff here, and then I'm going to write at the top. So let's assume that the matrix is, let's say, this one that we used in a previous example, 0, 1, 1, 0. The characteristic equation is the determinant of A minus C times the matrix 1 0 0 1. This is the identity matrix for 2 dimensions, right? This is the A is a 2 by 2 matrix, so I have to do C times I2 over here. This would be I2 is equal to 0, and that boils down to saying the determinant of what is A. Well, A is 0 1 1 0 minus, and I'm subtracting C times this, which is C 0 0 C. So this is the matrix that I want to set equal to 0, or the determinant of, and if you calculate here, you will see we get negative C, 1, 1, negative C. So this is the determinant that I want to set equal to 0. That boils down to the following equation. Now let's calculate determinants. So negative C times negative C is going to be C squared, and the minus 1 times 1 minus 1 is equal to 0. That is a quadratic equation whose solutions are plus and minus 1. So these are the two eigenvalues. And these are the only one eigenvalues because this turns out to be a degree 2 equation, and I cannot have more than 2 solutions. So that solves the problem of eigenvalues. Now, in general, and I'm going to close the video with this, if you have a matrix, and they tell you this in the book, if you have a matrix like A11, A12, dot, 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 A1n, so that indexes the first row, and the second row is A21, A22, dot, 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 A2n. And you can say dot, 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 we have n rows here, the nth row is an1, an2, dot, 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 a sub nn. Then the characteristic equation, which is A minus C times I equal to 0, the determinant, boils down to this thing where you subtract, because you subtract C times the identity, and the identity matrix has only non-zero entries down the diagonal, and they're all 1. When you subtract, you get A11 minus C, so you subtract C from the diagonal and leave the other entries the way they are, A12, A13, dot, 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 A1n. And then the next thing is A21, A22 minus C, A23, dot, 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 A2n, and so on. So you go down to the last row, which is AN1, AN2, dot, 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 ANN minus C is equal to 0. So this is the characteristic equation in general for an n by n matrix, and you have to work out this determinant, you have to calculate it, and that's going to give you a degree n equation, and you will potentially get a maximum of n eigenvalues. Now remember that you're looking for real number solutions. Sometimes these equations do not have real number solutions, and you might end up not finding any sort of eigenvalue if the equation has only complex, like purely imaginary solutions, complex numbers that are not real numbers. This is the general characteristic equation. In practice, again, what you do, you subtract C from the diagonal and you set the determinant equal to 0. Notice, and I'm going to close the video here, that in the book they do things slightly different. They say instead of A minus Ci, like we said here, so I said the determinant of A minus Ci, they will say the other way. Instead, they will say the determinant of Ci minus A. And also in the book, they use, instead of the constant C, they use the constant lambda. But again, if you care about this particular type of notation, you will write the equation as lambda times I minus A, and in practice that boils down to changing all the signs here in the equation and setting it equal to 0, which is the exact same equation. Thanks for watching.